Hello. For this micro project, the dataset we choose is War Robot Navigation, and the group members are Dongqing, Peidong, Huiyu, Kejia. For this dataset, the data were collected as the CITOS Group 5 robot navigates through the room following the wall in a clockwise direction for 4 rounds using 24 ultrasound sensor. It is worth mentioning that the 24 ultrasound reading and the simplified distance were collected at the same time step, so each file has the same number of rows. It has 4 class labels: move forward, slight right turn, sharp right turn, and slight left turn. There are 5,456 samples in our dataset, 24 features and a class label. We divide these samples into training set, validation set, and test set according to the ratio of 3:1:1. And after that, we create the dataset class. We create dataset class. This is memory efficient because all the features are not stored in the memory at once but read as required. We use the data loader. The data loader, which combines the dataset and the sample, and can provide multiple threads to process the dataset. This function is used when training the model to divide the training data into multiple groups. This function throws a set of data each time until all the data are thrown out. It is to do a data initialization. And in this part, we set PCA as false.
In the early time of the project, we built a single hidden layer network to help to understand the training and validation process. Since our dataset consists of 24 features, and the label is classified into 4 classes, so we set value 24 as the input of the network and 4 as the output. Throughout the process, we set that the learning rate is 0.001 and the time of iterations is 100. In order to explain our narrow network model directly, here we will use LAM to explain the model. First, we will define a prediction function, which will be used as the input of LAM afterwards. And what comes out is the probability of each category. Next, we create an interpreter to explain the following samples. In the notebook, we will explain the 5th sample. Finally, we will visualize the results. In the training process, we take the cross-entropy loss as our loss function. The optimization we use is gradient descent. As shown in the figure, in the whole iteration process, the accuracy of the validation sets starts to converge around 13 times, and finally converges to 0.87, and the final loss is about 0.11. From the results, the effect of this single hidden layer network is not bad, so we want to see if we can optimize the final results by increasing the number of network layers inside. So there is a second network structure. In the same, we set the input as 24, the output as 4. This time, it consists of 8 layers. The learning rate we use is still 0.001, and the time of iterations remains 100. As we can see from the figure on the right, the loss of our validation set reached its minimum value at the 17th time, and overfitting occurred in the subsequent iterations. And we found that the accuracy and the loss of this network structure are not as good as a single hidden layer network. This means that if the number of network layers is too large, the network performance will decrease due to gradient attenuation.
Why does neural network need activation function? If there has no activation function, the output of each layer of the neural network is a linear function of the upper layer input. No matter how many layers in the neural network, the output is a linear combination of inputs. This situation is the most primitive perception. Therefore, a nonlinear function is introduced as the excitation function, so that the deep neural network can approximate any function. The goal of the activation function is to increase the nonlinearity of the neural network model. So in the process of training neural network, one of the important hyperparameter is the activation function, and we need to make a choice regarding which activation function to use in hidden layers. And then I will introduce some common activation functions. The first one is Sigmund function. Here is its formula and function image. The Sigmund function can map the input value between 0 and 1, similar to a normalization operation, but it has a disadvantage. It is easy to cause the gradient to disappear. It means the gradient value from the input layer to become smaller and smaller during backpropagation, even equal 0. And the second one is ReLU function. The ReLU function can resolve the gradient vanishing problem. The calculation speed is very fast, and it only needs to judge whether the input is greater than 0. The convergence speed is much faster than Sigmund. But it also has its shortcoming, dead ReLU problem, which means that some layers may never be activated, resulting in the corresponding parameters never being updated. In order to resolve the dead ReLU problem, we propose to set the first half of ReLU function to be non-zero, which is called the decay ReLU function. And now through the graph in the left, we can see that the curve obtained using decay ReLU function is smaller than that of ReLU function. And we can also see that the result of using the ReLU activation function. Now the epoch is set to 200, and the accuracy is more than 90%. And we can find that the results of using decay ReLU function and the ReLU function are both good. They are faster than the Sigmund function.
Then, we have built 3 networks. The net1 and net2 have the same activation function, Sigmund, but net2 is deeper than net1. Net3 has the same structure as net2, but with ReLU activation function, and we plot the average grading and the difference of parameters by layer. Look at the graph. We can find that there is a vanishing grading problem for the net2, which is deeper and with sigma activation function. First, the gradients of neural networks are found by using backpropagation. That is, the backpropagation finds the derivatives of the network by moving layer by layer from the final layer to the initial one. And by the chain rule, the derivatives of each layer are multiplied down the network to compute the derivatives of the initial layers. For example, this is a derivatives for simplified 3-layer networks. And for the sigma function, for all x, the derivation is smaller than 1/4. So, the gradient decreases exponentially as we propagate down to the initial layer. And a small gradient means that the weights and the biases of the initial layer will not be updated effectively with each training session. According to the mini project, we have learned how to build neural networks and train it for classification task with Peidong, who has 2 main features: an n-dimension tensor similar to NumPy but can use on GPU and can automatically differentiation for building and training neural networks, and some efficient tools like class dataset, data load, and we have compared the performance of different activation functions. And finally, we have 96% accuracy for the classification task. It is quite good.